All right, what do we got? So we are doing block pulls pulley. I think is number 3 on your sheet. I might be wrong though, because I have an old version of the worksheet here printed off because I'm dumb. But so the idea behind this block pulls pulley problem is you've got, your ceiling with a pulley hanging from it. All right, and the pulley is not massless. In other words, it has mass, and then there's a block hanging from it. All right. And so what do we know? Let's take a minute and write out our givens. So first of all, the pulley, let's write out all our givens. So for the pulley, we know that the mass is 2.4 kilograms. We know that I did not give you the radius. All right, we do know that it has a rotational inertia because it's a disk about its center of 1/2 mr squared. All right, and then the block has a mass, little m, of 0.5 kilograms. Okay, string wraps around the perimeter of the pulley, block is released, no slipping, blah, 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 blah. We gotta find the tension in the string. Okay, so we've got two moving things. We've got a pulley and a block. The pulley is going to be rotating angularly, and the block is going to be moving linearly. So all I'm going to do is I'm going to write a net torque equals net torque equation for the pulley, and a net block or a net force equals net force for the block. All right. So for the pulley, here's what we're going to do: net torque about the center of mass equals net torque. So let's see. So I alpha. So let's see. I is 1/2 times mr squared, so there's my I, times my unknown alpha, equals the net torque. Well, the only torque is going to be provided by the tension, right? So we're just going to have a net torque is just going to be the tension. I'm going to use T for tension. Oh, maybe I shouldn't do that because T and torque looks very similar. Let's call it FT, as in force of tension. And then my lever arm is just the radius, right? All right. So shoot, my R's don't cancel here. Okay, so remember, this is that trick that we used in the last one. Remember, because the rope is not sliding at the outside edge of the pulley, the acceleration is equal to alpha R, which means alpha is A over R. Okay. So now, hooray, all of my R's cancel, right? So R's, 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 and so what I've got now is 1/2 MA equals tension. And since I knew that capital M was 2.4 kilograms, that means my tension is 1.2A. Okay, just by plugging in the mass here. All right, so that is equation number 1. All right, so make a mental note. I'm going to erase. I'm going to write that down. So we know FT equals 1.2A. All right, so we have figured out that our tension is 1.2A. All right, so that was derived by considering the pulley. Now let's consider the block. So the block has two forces on it. It's got a mass of 0.5 kilograms. Gravity is going to pull it down with a force of 4.9 newtons. And then we've got our tension. All right, and so if I do net force equals net force, let's see, I get mass times acceleration. Now, here I'm assuming that my tension is positive, which is going to make my acceleration positive, right? Basically, everything's going to accelerate this way. So anything pointing in that direction, I need to make positive, which means my tension over here is going to be negative and my gravity is going to be positive. So I've got 4.9 minus tension. Okay? So now we've got two equations, right? We've got equation number 1, which was obtained by looking at the pulley, and equation number 2, which was obtained by looking at the hanging mass. Okay? So now what we can do is just solve. We got two unknowns, two equations. So probably the easiest thing to do would be to take my tension and plug it in over here, right? Just, all right, and so what we get if we do that is 0.5A equals 4.9 minus tension, 1.2A. So add 1.2A to both sides, and you get 1.7A equals 4.9. So we can solve for our acceleration. Turns out to be 2.88 meters per second squared. And so now I can plug that in here to find that my tension is 1.2 times that, which gives us 3.46 newtons. Okay, so there we go. That is that.